All right, I'm going to do an example problem that I actually have a lot of fun with. And because I'm a physicist, I'm giving you a physics problem. Now, granted, bear in mind that you don't actually need to know how to set this problem up, but rather how to do the calculus portion of this. But I'm going to go through and walk you through setting up the problem anyway. All right, so we have a box. Here's the box. And this will be a box of, let's see. I don't know, fish, I guess. I don't know. What kind of box do you usually say? All right. Oh, you know what this is? This is the giant IKEA box that I had to pull around. That has my wife's cabinet. And I had to pull this thing around, and so I attached a rope to it, and I'm pulling it, and I'm trying to yank it into the car. And apparently I couldn't find a cart, so I'm dragging it along the floor. Okay. So I'm pulling up at an angle of theta. And then what I do is I say, all right, well, I know there's some forces acting on this box. Well, one force, obviously, is the force that I'm pulling it up at. We'll call that F. And the other force is, there's a force that the Earth always exerts on the box no matter what, and it is called W. Also known as the weight. There's the force that the ground pushes on the box, and it counteracts weight, basically. It is called the normal force. And then finally, there's another force that is pulling against me, because this is not an easy box to pull. If I had this on ice, it would be much easier. Whereas I have this on concrete, it's not as easy. Or say asphalt, that's even harder. That implies to you that basically a big difference in pulling this box around is friction. So we're talking about friction is the last, I'll call it the force of friction. And there's one physics thing that you need to know, and that is the force of friction is equal to the normal force times this coefficient that we call mu. And mu is just a measurement of how rough the surface is. For example, if mu were really small, then you're probably dealing with ice. Whereas if mu were, or if the materials you're dealing with is like rubber or asphalt, then you're probably dealing with a very high mu. It's just a number. It has no units. It's just, 0.5 or something like that. Now, let's figure out, well, what is the force? Okay, so what we have to do is we have to break these things up into their x and y components, and the only thing that's actually in some kind of funky orientation of their x and y components is this f. So I'm going to break this guy into f of x and f of y. And using good old trigonometry, if that's theta over here, then f of x is equal to f times the cosine of theta, and f of y is equal to f times the sine of theta. Cool. All right. Now, what I'm going to do is I'm going to add up all the forces in the x direction, and I'm going to add up all the forces in the y direction. And usually what I do here is I set them equal to 0. And then what I do here is I use one equation to kind of help me get the direction to solve out for the other equation. So if I'm talking about the forces in the x direction, I have my force in the x direction. That would be the x component of this force up here. And the other force that I see in the y or the x direction is f of f. So I'm going to say I'm going to subtract f of f. And why did I subtract it? Well, it's because it's going in the backwards direction. All right. Now, as far as the y direction goes, the vertical forces, I see 3 of them. I see this normal force, I see the w force, and I see the f of y. So I've got normal force going in the positive direction. I've got f of y going in the positive direction, which is also known as f sine of theta. And then the W is minus W. Cool. Let me just kind of set what this is equal to. This is F cosine of theta minus the normal force times mu, because I told you that F of F is actually normal force times mu. Now I know that you guys are thinking, oh my goodness, this is so crazy. And like I said, you don't need to know how to set this up. That would be, if you were taking first year physics, that's what you would have to do. Let's see. I'm setting this equal to 0, and I'm setting this equal to 0. So this first equation tells me that F cosine of theta is equal to the normal force times mu, because I just brought that over to the right side. And this is second, and I'm thinking, oh my goodness, I don't know what n is. Well, actually, you can use the information from here to figure out what n is. So I'm going to pull this stuff to the right side of the equation. So the second equation gives me n is equal to W minus F sine of theta. Cool. So I'm going to plug that n into here, and now I have F cosine of theta is equal to W minus F sine theta all times mu. Let's distribute that mu in there. And remember, you guys are thinking, oh my goodness, that's so much writing. Well, don't wimp out on me. It's not particularly hard. It's just a lot of writing and organization. All right, and then we have, let's see. I need to get F all by itself, because that's what I'm trying to solve for, right? So I have F cosine of theta plus mu F sine of theta is equal to mu W. Let's go up here. I'm going to pull out an F because it's in both of the terms on the left side. So I have F times the cosine of theta plus mu sine of theta is equal to mu times W. Then I'm going to drop kick this guy downstairs over here. So I have F is equal to mu times W over the cosine of theta plus mu sine theta. Awesome. I'm done. Actually, no, I'm not done. I just set up the problem. This is the calculus problem we want to solve. We want to take the derivative of F with respect to theta, dF d theta, and figure out how the force will change as you pull at different angles. Cool. All right, so let's now this above this squiggly line is physics. Below this squiggly line is calculus. Now, a physicist needs to know both of them, but a calculus student doesn't necessarily need to know physics. Actually, let me explain to you the story of how they're related, and I've just turned this into a more than 10-minute video. And you know what? Let's go through it, because the stories are interesting. All right, so Newton came up with physics. Isaac Newton. He was like, all right, you guys, I had an apple fall on my head, and I got smart, and this is how I want to explain the world. So he came up with physics. Now, the big wigs of the time said, Newton, you're crazy. The math for what you're suggesting doesn't even exist. Why are you spouting off these crazy equations when there's no math for it? And then Newton said, okay, well, give me a second. And then he came back like a week later. I'm making up the part of it actually being a week. I have no idea. But he came back at some time later, and he said, okay, hey, you guys, I got this new math. It's called calculus. And it will explain all the physics that I tried to explain to you last week. And then they read the calculus paper, and they said, oh, my goodness, that makes sense. And then they applied it to physics, and they said, oh, my goodness, I want to have, and so then they all threw apples at each other, trying to get smart, but no one could do it because Isaac Newton is just, crazy smart. I embellished the story a little bit, but basically that's how calculus and physics are related. They're actually two sisters of the same father. All right, dF d theta, And there, we have officially turned it into over a 10-minute video, which, you know what, deal with it, you guys. This is fun. This is fun, right? You guys are having fun. I'm having fun. All right. Let me just kind of double check my notes here. And, all right, let's take the derivative of this. Now, we've got a quotient rule happening here. And I'm going to take, it was... And notice how every single time I write or I do the quotient rule, do you guys notice how I write out my instructions to myself and then I do it? I know it's an extra step, but you know what? It keeps me organized. It helps me out. All right, so it was low D high minus high D low all over low low. All right, so low D high, so that would be the cosine of theta plus the mu sine of theta. That is simply the low part. Now I need to do the derivative of mu w. All right, and then minus high d low. So that would be high is the mu w times the derivative of the bottom. So that would be cosine of theta plus mu sine of theta, all divided by cosine of theta plus mu sine of theta squared. The nice thing here, see this first thing right here, this guy right here? Actually, let me start using a different color. This thing right here, this is saying what is the derivative of mu w with respect to theta. The problem is theta isn't even in mu w. Mu is a number, w is the weight. It has no dependence on theta. So what it's asking you is how does mu times w change as theta changes? But there is no mu or theta in mu times w, so that answer is 0. So guess what? If that's 0, then what's cosine of theta plus mu sine theta all times 0? Well, that whole thing's 0. So I'm left with just, the straight up negative, whatever. Let me see. That would be... I need to take the derivative of this part. Okay, so I have negative mu w times the negative sine of theta, because that's what the derivative of cosine of theta is, plus mu times the cosine of theta, all divided by all that junk on the bottom, all that junk in the trunk. Let's distribute this mu in there, and I think that's my answer, to be honest with you. Or I'm sorry, the negative. That's what I meant. So I have mu w times the positive sine of theta minus the mu cosine of theta all over cosine of theta plus mu sine of theta squared. That, my friends, is the df d theta. Now, quite often, what we want to be able to do in this is we want to set this equal to 0. We want to try to usually when you're taking the derivative of with respect to something and then setting it equal to 0, you're trying to optimize it. So if we let this equal to 0, df d theta equals 0, then what happens? This is part B. Then essentially all I need to do is the numerator divided by the denominator equals 0. So basically the numerator equals 0. So it's mu w sine of theta minus mu cosine of theta is equal to 0. Actually, I think I need a parentheses in there to make my thing complete. Okay, so I'm going to divide both sides by mu w, and that basically kills it, because 0 divided by mu w is still 0. And I have sine of theta is equal to mu cosine of theta. And I'm going to divide both sides by cosine of theta to kind of get things on one side. So I have the tangent of theta, because that's the definition of sine over cosine, is equal to mu. And so I want to figure out what theta is. I just take the inverse tangent of both sides, and I have theta is equal to the inverse tangent of mu. All right. So if you, what is that saying? What is that physically saying? That's saying that if you pull at an angle that is the inverse tangent of the coefficient of friction, then you are pulling, I believe, with the smallest amount of force, or it could be the biggest. It could be the smallest or the biggest, and we need to do a little bit more analyzing in order to actually figure out what it is. But you could be pulling with the smallest amount of force that you need to pull. So now we actually have something helpful to us. And I know that you guys are thinking, well, just put your IKEA box on wheels. Okay, fine. What if it's not an IKEA box? What if it's a building or something that giant that we need to pull? And we need to say, all right, it's almost impossible to pull this thing. And if I pull it up like that, it's not really going to help me. If I pull it straight like that, that's going to make the coefficient of friction much bigger. Now, if I pull it at some angle and I don't know what that angle is, then I will be pulling at the least amount of force that I need to pull this at, and that might help me a lot. And then some brainiac, or actually you, come by as, you know, trained engineer or whatever, and you say, well, I'll tell you what that angle is. You just take the coefficient of friction, and we can figure that out with to be honest with you, I usually do a lab where I figure out the coefficient of friction with your shoe and a wooden board. That's all you need for the lab. Anyway, you can figure out the coefficient of friction, then you take the inverse tangent of that. That's the angle you pull it at. Now give me a bunch of money, because I just saved you a whole lot of money and time and energy in solving this. And you know what? They will give you lots of money if you can come up with answers like that. That is the application of calculus, my friends. It is amazing. Have a wonderful day.